the afternoon session today. Our first speaker, Antonio Viruel from University of Malaga, who will talk about path partial groups.
Thank you very much. Well, so I guess it's traditional. I have to thank the organizing committee for carrying so much on the details that I feel like home all this week. So, and then just one little thing. So this morning when Ivo was saying that he have stolen this logo from the CRM. So I remember that I got something that probably most people don't know, that is one of these, oops, I don't know, no, very bad, like that. So this is, I guess, the very first time that the logo of the CRM show up in a t-shirt that is, I guess, 30 years old or something like that. And is one of the finest mathematical objects. Is a finite model of proper group actions for a free group of rank 3 originally. Now is rank 4, I guess, because I have a few holes. But well, so let's talk, let's start about the thing. So, well, after these so many thoughtful and deep lectures, so today I'm just addressing a kind of easy question. Easy question that somehow trace back to the origins of group theory and representation theory. So fix category C, and then the first question, well, let's say given X, any object in C. So the first question is, what's out C of X? Unless you are a mathematical Taliban, you will say it's a group, right? And if you have any concerns about sec theoretical things like well, that may not be a set. So just let's claim that all the categories are going to use today are going to be locally small. So it's going to be a set, invertible elements, blah 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 blah. So it's a group, and indeed, this was the way somehow groups show up in history, and that is somehow we always think groups, right? And even I guess most of us, at least one in a lifetime, we have said, well, I do study symmetries. So we always think of groups as automorphisms of groups. So the second kind of not so trivial questions is which groups are so represented, right? And that is kind of a tricky one because, you know, we have fixed the category C. And although I guess most of us know how to represent groups as the full group of automorphisms of some object, then the question is whether you can do for all groups in just one fixed category, right? So that deserves a special name, and if every maybe finite group can be so represented, we say that C is, if it's only for finite, I would say finitely universal. So identifying universal categories is a really hard problem, right? So, oops. So, for example, let's say inverse Galois theory. We still don't know whether the category of a rational, of a Galois station over the rational is finally generated, right? So the next time that Gunther shows up in the lecture room, you can ask him about this question. So, but we do know some other cases in which the category set universal. So if you take the category of a simple non-oriented graph, or even if you think that as just B-oriented equators, then are universal. And then if, well, if we think of what seems to be the most popular category this week in this lecture room, if we think of groups, group is not finitely universal. So it's indeed not universal. So for example, there is no group G such that when you calculate the group of the full group of automorphisms of G, that happens to be the cyclic group of an odd number of elements, right? And it's funny, it's an interesting, easy but tricky question. Try to prove this, and then the problem happens that the main problem is that groups are too symmetric. Right, what happens is that, well, for any group, we get this thing, which can be identified with the inner automorphisms of G, is a normal subgroup out of G. So essentially means if you start with something which is not abelian, you start having a lot of symmetries. And if you start with something which is abelian, you must always have an involution. Either the group is trivial, or you got the minus identity, which is group morphisms for abelian groups. Or if you start with an elementary abelian group and it's not C2, then you can always swap two generators, right? So that's somehow the reason why you cannot get groups to be finally universal. But funny enough, the thing is that it's so related with the fact that we got inner automorphisms that if there is a theorem by Troster, I have to read the names because otherwise I will just mess up. They say that every group G is such that for every, I will write better. For every group G, there exists K simple group such that when you consider the outer automorphisms of K, you get G, right? So that somehow means that groups are not finally universal, but there is a quotient category of the category of groups. If you consider just the category of representations, that is finally universal. So then the natural question is, the problem is somehow how close we can get to groups to get something which is universal. So the problem would be find a group embedded in some category C, a full embedding such that C is universal. And so this is the problem we are going to address. And well, all this started with almost a year ago in the very last on person conference we had in Malaga when Remy showed up and asking about these kind of questions, and we start working and finally solving. And so our first theorem today will be, let me call theorem A because it's going to be a kind of a simple version of it. It says that partial groups is a universal category. And recall that so we got groups inside partial. Oops, sorry, inside partial groups, full, and part is universal. Okay, so so this is kind of this is version of the theorem we are going to prove today. So
sorry, can you just explain what universal means in that context of partial groups?
So yeah. So yeah. That is, for every group G, there exists P, a partial group, such that out of P is isomorphic to G.
Excuse me, Antonio, what do you mean by partial group?
Wait 5 seconds. 1,
yeah. Okay, well,
2, 3, 4, 5. This is a partial group. So so partial groups show up in the work of Andy Chermak trying to prove that
I see.
localities or centric linking systems.
Okay, thanks a lot. I didn't notice this. Okay, thanks a lot.
Yeah, don't worry, Mark. Yeah, it was okay. So I'm just going to, I'm not going to get into way more detail. We already heard a little bit about that in the.
Okay, sorry, I interrupt you. Yeah, okay, yeah. Please, take your time. Continue.
Yeah, but I'm going to explain it in any case. So
good.
So well, they show up in the work of Andy Chermak about these things. I'm not going to get too much into detail, but essentially, as Ellen said, a partial group is a tuple like this one, right? So, and then if you want to think how close this is with a group, right? So this will be somehow the set in which the partial group structure.
Okay, thanks.
So then this DEM is just the words you can multiply, right? So in particular, the elements of the groups can be multiplied, of course, and wherever you get a concatenation of 2 words in there, any of those have to be. In particular, the empty word have to be there, which is going to be the unit in the group, right? And then this multiplication. So it's like the identity of the elements. So they are not multiplying with anything. You get the same thing. So, and then the second property is like associativity, right? So you can just either multiply 3 of them at once. So first 1 in the middle, and so on, right? And while multiplying the empty set will be the unit, as we said. And also there is an inversion that is like a map of an evolution on the group on itself. It's not to be a group morphing of anything, and then essentially what you do is just invert things, right? And then the only thing is that the product on the elements you can multiply, and the inversion behaves in the way you think, right? So whenever you multiply something by its inverse, to get one, right? And then, so this is the category. I mean, these are the objects, and then I have to define which are the morphemes in there. So the morphemes are just well, so like it would be groups. You get a set map between the set defining the group, and then it have to induce. Then we call this D was kind of a subset of the words of M1. So this C can be extended here, and essentially things that can be multiplying in M1 can be multiplying in M2. And well, as you expect, you can either multiply before doing psi, or you can just first multiply and then do psi, right? So there is a notion also of automorphism. So it makes sense. So it makes sense. Well, these are kind of locally small categories again. So if like this pi minus 1 partial group, then again out M is a group, is a group, and then each groups are these, right? And recall, of course, the category of groups is a full category of partial groups, right? Because essentially for groups, what you do, G, what you do is just M equals C, T are just words on G, P is a standard multiplication, and this is the inversion state, right? So how anyone can construct a partial group with a given group of automorphisms. So this could be a kind of technical. So I will start just making a kind of intuitive proof of theorem one. So what we're going to do is just define these path partial groups that show up in the text. So we define path partial groups. And I want you to keep in mind that idea of path algebras we already saw in Henning Krause's lecture. We briefly saw that, right? But you saw that there is, whenever you got a quiver, you can define an algebra in there. So let G with vertex set V, edge C, P, R. It's going to be a kind of constructive thing. But I'm just trying to be here intuitive, and so you can follow what we are doing. So I will start saying that this is a quiver, like if I was going to construct a path algebra, right? So then I want to define n of G, and again I have to define something n, some D, some product, and some inversion, right? So let me make room for everything. And well, if I want this to look like a path algebra, so then the set of elements I can multiply, they're just paths each, right? So then D, well, even better. So elements will be path in G, and then the multiplication will be just a path concatenation. But you know, the fun thing is that when you define graph algebras, whenever you got two arrows that cannot be composed in the path, in the quiver, you define that product to be 0, right? But then we don't worry about that because we don't have a 0 element there, and moreover, we don't need to multiply everything. So we do path concatenation if possible, right? So that means that whenever you do that, then D is not every word on path. So you just consider words in which path can be concatenated. So this will be kind of a P1, Pn, working paths such that they can be concatenated, right? Somehow the n of pi equals the source of pi plus 1, right? So you should be able to concatenate this path. Well, then the next thing, so we already got this, so we need an inversion. And then, of course, the inversion you're going to consider is just orientation reversing, right? So, okay, let me just make even more room here because I'm going to make some. So, and recall just that the things that the inversion should make paths into paths, right? So essentially, or if I must have orientation reversing in every path, I should have orientation reversing in edges, right? So if I have orientation reversing in edges, means that every edge is B oriented. So essentially, this is not a quadrant; it have to be a graph, right? Edges can be reversed. So then G is a graph. So I can just go up here and delete. Oh well, I will just red, no quiver. It's going to be a graph, right? So what else? In particular, if P is a zero length path, so essentially we got a vertex, right? Then P minus 1 have to be 1. Sorry, V minus 1 have to be V, right? So it's not only that the graph is reversed, so also the vertices are evolution in this new partial group. So we need to be careful about how we make things here. So the very first thing is just first we can delete this not only paths. So paths are just well, all right. Paths are just the same of sequences of vertices, right? And so this is essentially, we got words on V, right? And then we got an extra relation. That is here, right? So this is not going to be words in the free monomial on words of on the vertex X. So, but we have to divide by G equals this one, right? So they are indeed, so they are indeed reduced words in here. Okay, so just so reduce words in the free in the monomial of free words plus the relation every vertex is the itself inverse. What else? Now, assume you get a path like this V1, Vm, right? And then choose any other edge, which will be Vm plus 1, right? So this path can be concatenated. So I should be able to multiply P E, right? And what happens is that, well, you get V1, Vm minus 1, Vm, well, when I'm just multiplying, so, well, first I'm going to multiply this, Vm plus 1. And when I do all these things, what I get is V1, Vm minus 1, Vm plus 1, right? So this will be the product in here. And, well, these have to be a path, right? So that means that there should be an edge in here, right? So it's not just paths, but then path should live in clicks, right? So again, it's not that here we are going to have a reduced word, but what we have to do is just to take union. We get all C's inside V clicks, and we consider reduced words in the monomial over C quotient V equal V minus 1, right? And then here will be union of free words on the reduced words on clicks over this thing. Oops, this is not here. So this is here, and this will be path concatenation. So that's going to be a path partial group, right? So given any graph, we're going to define as a set, we're going to get for every click in the graph G. So click means that these vertices generate a complete graph. So we are going to get reduced words in those things. Then, since these are just paths in a click, so that means that every two paths are concatenable in a complete graph. So we get this thing, but still, if you do this, you still can have inner conjugation, right? So finally, you want to get rid of inner conjugation. So you exclude things like vertex, path, vertex minus 1. So this will be vertex V1, Vn, V. So you don't want these things, you don't want those things to be in M, right? So here, instead of taking now only reduced words, what you have to take is cyclically reduced words, right? Well, so finally, so well, notice that, well, let G be any graph, G be a group. Let T be in a simple graph such that out of G is isomorphic to G. And let MG be the path partial group as the final graph. Well, so now notice the first is that, of course, V are just vertices are path zero, path of length zero. So these are just inside n of G. And moreover, vertices are the only group-like elements in N of G, right? So group-like elements, so means that elements that generate a cyclic group in the partial group, right? So not every element can be multiplied by itself. So these are elements that can be multiplied by themselves, and indeed they do produce symmetry. So they are involutions. Well, it's not going to be the first ones, the only thing. Notice. Well, so now, given F, an automorphism of our graph G, then F can be seen just a map from vertices to vertices. So for each vertex V, we got FB and define MF that goes from MG MG given by vertices to F of vertices, right? Since V inside MG generates NG, this can be extended to a unique partial group. Morphism. And moreover, since V comma W is an element of D. G if and only if, well, VE is an edge. So this PVW is defined if and only if PW is an edge. Then M of F of the sequence BW will be F of V, F of W, and since F is a graph morphism, then this also again will be in D of G, right? So essentially, so NF, well, I say for two, but it could be for any path. So NF is indeed from MG to MG and has inverse and F minus one. Recall that F was an element, an automorphism, right? So that gives me a maps from out of G to out of N of G, and it can be seen that it's a monomorphism, right? And to get an inverse, given now C, an element will be that it will be an automorphism of this path partial group. Then C maps group-like elements to group-like elements, and therefore, well, the only group-like elements are the vertices of the graph. So, and therefore, it uses some F from V to V given by V to C of B, right? And F maps every edge VW. So composable elements D of G to C of V, C of W, composable elements P of V, P of W inside G, because it's a path partial group automorphism. So composable elements should be two composable elements that is an edge. So F is a graph morphism. Right. So out of N of G is isomorphic to out of G that was isomorphic to our original G. Right? So this is the kind of conceptual and intuitive proof of theorem A, right? It's just constructing a kind of geometrical path group, path partial group that still have the same group automorphisms of the graph you start with, right? So just a remark for people who are interested in these things from the point of view of fusion systems. So these are not objective partial groups. Right. So if you think that objective partial groups should be really close to finite groups, then finite groups will have inner conjugation, and we are getting rid of inner conjugation. So these are not, right? So we are fine, right? So now then, a high-tech. Well, anyone is still awake, or have any question? Yes. So I see hands rising. Good. So now a high-tech proof of theorem. So indeed, theorem is a very particular case of a more general result. So let take a graph B, the category with well, I have to define which are the objects, and then the morphisms. So the objects are going to be pairs of G H, where this G is an element in graph. So it's a simple non-oriental graph. And H is going to be a collection of groups, non-trivial groups, indexed by the vertices of them. So these are kind of decorated graphs. So it's a standard graph, but we have put one group on each vertex, right? And then morphisms, the obvious one, right? So anytime you get a seed that goes from G1, H1 to G2, H2, right? So that means that we get C is just F V indexed by V1, probably just to recall that this one is just because this is the vertex X of this thing, right? And such that F from G1 to G2 in graphs, and FV goes from HV to H F of V in groups, right? So any morphing between decorated graphs is indeed a graph morphisms that maps each vertex group to a vertex groups, right? So theorem B. There exists a functor, I will call it M again, that goes from decorated graphs and embedded in partial groups. Moreover, if we consider the subcategory tech wraps and say finite, so the HPs are just not only groups, but they are finite groups, right? We get the following exact sequence. So we get that we get a product from V in V of out of HP. This thing injects in out of MTH, and this thing goes to out of G. Not exact, right? In general, it's not exact. If moreover, HV equals a fixed H for all V's in V, then the sequence above is split and exact. So, yep. So one was asking something? No? 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 Okay. So essentially what happens is that the automorphisms group of this object GH is just a brave product of out of H, this H, which is the same for all the vertices, and then you get a brave product with out of G, and then you have to think that this guy is indeed a permutation on the vertices, right? So this permutation is acting, permuting as many copies of this as the vertices have, right? So this is the high-tech theorem, and just a few remarks before getting into somehow the proof of that thing. So remarks.
So Antonio, can you hear me?
Yep.
Okay.
No, we didn't understand the sequence when all HB are the same group A. You said the sequence above is a split and exact or not exact.
And is exact. So I mean, yeah, it split because it is exact, right? Okay, so I'm just, my English is not that good, so it's a split.
You said the following exact sequence is not exact.
So, in general, this sequence is not exact. In general, it's not necessarily exact. So it's I mean, it's not a short.
Great, thank you.
Thank you. Yeah. So saying it is short, but it is exact, but it is not exact. Yeah. So if it will be proof, I can prove anything, right? By contradiction. But okay, so it's a non-short exact sequence. So it's an exact sequence, but it's not short in general, right? So it's only short whenever all the groups you get in here are just the same, right? So essentially, well, it's not that true. So essentially, what you want are the orbits of the out of G action on the vertex set. So in each of those orbits, you need to have the same group, right? Because this thing is moving the vertices. So whenever it is moving the vertices, you should move these groups too, right? So whenever one vertex V is moved to V1, H of V and H of V1 have to be isomorphic too, right? So in that way, it's not so it's exact but not sure. And just one quick remark that groups get into decorated graphs, right? Full as taking any group G, or I will say just H, just to follow with the notation. So it maps to the graph with one vertex, no edges, and H, right? So that makes this inside full, right? So we get groups inside decorated graphs. And then this thing, two partial groups. And then the funny thing is that this thing from here to here is again full, right? So this is full, this is full. And then the image of the image of this thing, the image of this thing is universal. So indeed, it's not necessary that you get to partial group, but to the image of this thing, right? So and graphs get into M of decorated graphs full, while M of decorated graphs is universe. So let me just quickly prove so essentially what we are going to make is just what we did for the intuitive idea of path partial group, and we are going to do it here, right? So now no path, no vertices, just group elements, right? So given a graph G, V, edges, and a decoration we define an N of G in two steps. So the first one is just, remember, we were just considering path in clicks, right? So for every C inside V, a click, define MC to be MCDC, proud of taking inverse. So MC is just cyclic reduced word in the group HC, where HC is just the free product of every element in the clique of the H, right? So we get, just think that instead of vertices, we get elements in the group HSB. So we get concatenations of those, and we want, if we got two elements in the same vertices, we can multiply them, but we get cyclically reduced. We cannot finish in the same group to start with, right? And then D of C are just words in N of C, such that, well, so to be, so these are just P1, Pn in words in MC such that when we make the multiplication of P iota to Pk, this again is in MC, or 1 less or equal than iota less or equal than K less or equal than 1. Right? So they are just sequences of group paths somehow, that whenever we get a subsequence of there and we make the multiplication, which is just a multiplication in HC, and then this is inverse in that free group, right? And then once you do that, just let the delta of C to be the deposit of cliques in G, and define N of G to be the colimit over delta of G of those MC that we have constructed. So this is Chermak. Colimit in partial group. Because inclusions do the right thing. So then N is obvious morphism. And if G H is indeed an object in decorated graphite, then the same way we did with the partial group, so the HV are inside MDH, right? Are the only proper, or honest, better say, the only honest subgroups, honest finite subgroup of MGH, and 2 the subgroups HV generate as partial group. All in GH, right? So then every F out of a G that maps E to FV and HV isomorphically to HV gives rise to an element in out of MGH, right? And if I get again an element in out of MGH, phi maps on its finite subgroups to finite subgroups. So vertices, and composable elements composable elements. So edges to edges. That is, it induces some F and automorphisms of the graph we start with, and moreover, be restricted to one of those honest group should be an isomorphism to this vertex, right? So that's the way that so that's how these isomorphisms in here show up, right? And just to finish in -1 minute, corollary terminate, take HV to be sigma 2 for every V, and in V, so out of HV equals 1, right? We get the thing. So that's all. Thank you.
Any questions? There's hand raised. I don't read who is, but just go ahead.
Carlos, I cannot. I know that you are talking, but because I recognize your voice, but I don't know what you are saying.
You hear me now? Yes. No, I was saying I saw a hand raised, but
yeah.
Yeah,
Clara,
it's me. If it's only one, then it's me.
Yeah.
So in your when you were giving us the more down-to-earth proof of the theorem A,
yeah,
you start with a graph, and then you produce a partial group, and then if you start with a graph which realizes a given group as its automorphism group, then you get so. But I mean, there are more graphs than. I mean, what I mean is, can you recognize from the graph? What did I want to say? Yeah.
So there are so the points that it's not only one. There are infinitely many. There are infinitely many partial groups with a given group of automorphisms.
Yeah. Yeah.
Exactly.
And can you sort of is there a way to see
if they are isomorphic or not?
Yeah. Yeah.
Yeah. So essentially the proof. The proof, what that's the proof is just that you can read the graph out of the partial group, because every group-like element is inside one of the vertices. Either if you do the down to earth, as you say, proof, or the technical ones. So group-like elements identify vertices if you got with finite groups, and well, the points that in this construction of graphs with given group of automorphisms, you have many choices, because essentially what you do is just a Cayley graph, and then you make an arrow replacement. So a different arrow replacement gives rise to different partial groups.
Okay. Yeah. Thank you.
But then, so that brings another question that I didn't mention, that once you get this, one of the funny problems you can do is just take your favorite graph theoretical problem and try to express or to characterize that graph property in terms of algebraic properties of the partial group that you end up with. But that will be another question. So Ele is also.
Ask a question about infinite groups. Is it possible that you could? I've got an echo coming through.
I hear echo.
Yeah.
So
I was just
ln
wondering,
was half its own price, and
there is presumably an analog of partial group for where you make the L the underlying set and infinite, and then you can ask a question.
sorry,
about-
Jason, I can you just say again?
Yeah. So presumably you can make partial groups with an infinite underlying set, and then you could ask the same question for infinite groups. Is that possible?
I didn't thought about that, but maybe. So I have worked in this kind of problems from two different, in different categories from different perspectives. So this one is just you get graphs into the category you want to work with, right? So the one you're asking me is just the other technique. You start with some object that have a G action, and then you put some flags or some critical point or something like that in the points that in order to identify orbits, right? So essentially, what you claim is that probably you start with the biset and then try to I don't know, delete some of the elements in some orbits to reduce all the possible automorphisms of that biset, right, or something like that.
Something, yeah. I mean, I'm just wondering whether you can have infinite partial groups.
Yeah, that's another strategy. So that's somehow when I have theorems like this one proving that vector fields over a manifold can describe finite groups, and essentially we do that. Just we put a group action on a manifold, and then we draw a flow which is a G equivariant, and then we put critical points on the flow. So we get flags somehow in every orbit. And here it should be the same. So instead of putting kind of a flag in there, like a critical point, you should kind of delete some points to get a kind of a singular non-existing orbit. So
okay, cool, thank you.
But I never thought about that point. And Ellen is just asking something.
Yeah, I just have a comment. So a PhD student of mine, Eduardo Salati, pointed out to me that there is some problem with Zermak's construction of co-limits. So I don't know exactly what is needed in your proof. I think it's probably not a problem, but perhaps you want to look into that.
Well, essentially, it's agreed with taking co-limits like Andy does. But essentially, what we do is just taking co-limits at the set level and the co-limits with words. Right? So essentially, that was at the beginning of our construction, not using Andy's co-limit and do it at the set theoretical level.
Okay, so you don't actually need this stuff.
No, we can just read, but it's nicer just to refer to some other.
I mean, actually, I think Eduardo wrote a short preprint on this, which he's going to publish. So perhaps you want to.
Oh yeah, so if you send us that reference, we will be glad to read it.
Okay.
Thank you.
Thanks.
Thank you.
I think we stop here, and we thank Antonio again for this nice talk.